A standing wave is a special kind of wave that doesn't move as it vibrates. In contrast with sound waves and light waves, which can travel through the air, the wave created in a guitar string allows the string to vibrate, but the guitar string itself doesn't travel across the room. Standing waves have two distinct parts, nodes and antinodes. The nodes are the part of the wave that doesn't move, that's in a fixed position, while the antinodes are the part of the wave that move up and down the most. Well, waves often have naturally occurring nodes, or the parts that don't move. Musical instruments are often designed to force a node, where the finger pushes down on the string. That prevents the string from vibrating. That's where your node is. By changing the distance between your nodes, or the parts that don't move, you can change the wavelength and therefore the frequency and the pitch of the sound the string makes. When looking at a wave created by a vibrating string, a complete wave will have 3 nodes and 2 antinodes. So by that definition, the top example here is not a complete wave because we only have 2 nodes and 1 antinode. To imagine a complete wave, you would have to imagine the string continuing on out into space. So in the first example, we really only have half of a wavelength contained in the string, while in the second example, we have a full and complete wave. These are examples of the first, second, and third harmonic. The relationship between the harmonic and the wavelength and the length of the string is the length of the string is equal to the number of harmonic times the wavelength divided by 2. In the top string, we would say the length of the string is equal to the first harmonic times the wavelength divided by 2. Or the length of the string is equal to 1/2 of the wavelength. And that's exactly what we saw before. In the second harmonic, we say the length of the string is equal to 2 times the wavelength divided by 2. The 2's cancel out, and we get the length of the string is equal to the wavelength. And we could use the same calculation for the third harmonic, where the length of the string would be equal to 3 times the wavelength divided by 2. Or the length of the string is equal to 1.5 wavelengths. And then if we highlight the wave, again 3 nodes and 2 antinodes, we can visually see that yes, the string contains about 1.5 wavelengths. When you're dealing with a string or a pipe where both ends are fixed or both ends are open, then you use the equation that the length of the string is equal to the number of harmonic times the wavelength divided by 2. However, if you're looking at a pipe where one end is open and one end is fixed, then your equation is the length of the pipe is equal to the number of the harmonic times the wavelength divided by 4. However, in this equation, the n has to be odd. It can only be 1, 3, 5, or 7, etc. In this problem, they give us the length of the string and the third harmonic, and they want to know the wavelength. It's a guitar string, so both ends are fixed. So we use the equation, the length of the string is equal to the number of the harmonic times the wavelength divided by 2. Or 1/2 of a meter is equal to the third harmonic times the wavelength divided by 2. We multiply both sides by 2/3, and we get 1/2 times 2/3 is equal to the wavelength, or the wavelength is equal to 1/3 or 1/3 of a meter. This problem is a bit more challenging because we're not told the harmonic. We're told, however, we're talking about 2 consecutive harmonics. And we can see that one harmonic is twice as big as the other. That only happens one time. That only happens between the first and the second harmonic. If we use the equation, the length is equal to n times the wavelength divided by 2, and just start plugging in random numbers. Hypothetically, let's say the length is equal to 10. If that's the case, 10 is going to be equal to the first harmonic divided by 2, or the wavelength is 20. In the second harmonic, we write the equation that the length of the string is equal to 2 times the wavelength divided by 2, or the wavelength is 10. In the third harmonic, we write 10 is equal to 3 times the wavelength divided by 2, or the wavelength is roughly equal to 6.7. And then again, in the fourth harmonic, we write that 10 is equal to 4 times the wavelength divided by 2, or the wavelength is equal to 5. And we could keep on going, but you'll notice the only time the wavelength is twice as big is between the first and the second harmonic. After that point, you never have a doubling between the harmonics. So we now know that we're dealing with the first and the second harmonic. The longest wavelength is in the first harmonic. So that means our 4-meter wavelength, that's our first harmonic. And the second harmonic is the 2-meter wavelength. You'll remember from our equation that in the second harmonic, the wavelength is equal to the length of the string. So if the wavelength in the second harmonic is 2, the length of the string is also 2.